In physics, the graviton is a hypothetical elementary particle that mediates the force of gravitation in the framework of quantum field theory. If it exists, the graviton is expected to be massless and must be a spin-2 boson. The spin follows from the fact that the source of gravitation is the stress-energy tensor, a second-rank tensor. Additionally, it can be shown that any massless spin-2 field would give rise to a force indistinguishable from gravitation, because a massless spin-2 field must couple to the stress-energy tensor in the same way that the gravitational field does. Seeing as the graviton is hypothetical, its discovery would unite quantum theory with gravity. This result suggests that, if a massless spin-2 particle is discovered, it must be the graviton, so that the only experimental verification needed for the graviton may simply be the discovery of a massless spin-2 particle. Theory. The four other known forces of nature are mediated by elementary particles. Electromagnetism by the photon, the strong interaction by the gluons, the Higgs field by the Higgs boson, and the weak interaction by the W and Z bosons. The hypothesis is that the gravitational interaction is likewise mediated by an as yet undiscovered elementary particle, dubbed as the graviton. In the classical limit, the theory would reduce to general relativity and conform to Newton's law of gravitation in the weak field limit. Gravitons and renormalization. When describing graviton interactions, the classical theory and semi-classical corrections behave normally. But Feynman diagrams with two loops lead to ultraviolet divergences, that is, infinite results that cannot be removed because the quantized general relativity is not renormalizable, unlike quantum electrodynamics. That is, the usual ways physicists calculate the probability that a particle will emit or absorb a graviton give nonsensical answers and the theory loses its predictive power. These problems, together with some conceptual puzzles, suggest that a theory more completed than quantized general relativity must describe the behavior near the Planck scale. Comparison with other forces. Unlike the force carriers of the other forces, gravitation plays a special role in general relativity in defining the spacetime in which events take place. In some descriptions, matter modifies the shape of spacetime itself, and gravity is a result of this shape, an idea which at first glance may appear hard to match with the idea of a force acting between particles, because the diffeomorphism invariance of the theory does not allow any particular space-time background to be singled out as the true space-time background. General relativity is said to be background independent. In contrast, the Standard Model is not background independent, with Minkowski space enjoying a special status as the fixed background space-time. A theory of quantum gravity is needed in order to reconcile these differences. Whether this theory should be background independent is an open question. The answer to this question will determine our understanding of what specific role gravitation plays in the fate of the universe. Gravitons. In speculative theories, string theory predicts the existence of gravitons and their well-defined interactions. A graviton in perturbative string theory is a closed string in a very particular low-energy vibrational state. The scattering of gravitons in string theory can also be computed from the correlation functions in conformal field theory, as dictated by the ADS-CFT correspondence, or from matrix theory. A feature of gravitons in string theory is that, as closed strings without endpoints, they would not be bound to Brownius and could move freely between them. If we live on a Brana, this leakage of gravitons from the Brana into higher dimensional space could explain why gravitation is such a weak force, and gravitons from other Branas adjacent to our own could provide a potential explanation for dark matter. However, if gravitons were to move completely freely between Branas, this would dilute gravity too much, causing a violation of Newton's inverse square law. To combat this, Lisa Randall found that of three Brana would have a gravitational pull of its own, preventing gravitons from drifting freely. possibly resulting in the diluted gravity we observe while roughly maintaining Newton's inverse square law. See Brenner cosmology. A theory by Ahmed Faraj Ali and Saryad adds quantum mechanical corrections to general relativistic geodesics. If gravitons are given a small but non-zero mass, it could explain the cosmological constant without need for dark energy and solve the smallness problem. Experimental observation. Unambiguous detection of individual gravitons, though not prohibited by any fundamental law, is impossible with any physically reasonable detector. The reason is the extremely low cross-section for the interaction of gravitons with matter. For example, a detector with the mass of Jupiter and 100% efficiency, placed in close orbit around a neutron star, would only be expected to observe one graviton every 10 years, even under the most favorable conditions. It would be impossible to discriminate these events from the background of neutrinos, since the dimensions of the required neutrino shield would ensure collapse into a black hole. However, experiments to detect gravitational waves, which may be viewed as coherent states of many gravitons, are underway. Although these experiments cannot detect individual gravitons, they might provide information about certain properties of the graviton. For example, if gravitational waves were observed to propagate slower than c, that would imply that the graviton has mass. Astronomical observations of the kinematics of galaxies, especially the galaxy rotation problem and modified Newtonian dynamics, might point toward gravitons having non-zero mass. Difficulties and outstanding issues. Most theories containing gravitons suffer from severe problems. Attempts to extend the Standard Model or other quantum field theories by adding gravitons run into serious theoretical difficulties at high energies, because of infinities arising due to quantum effects. Since classical general relativity and quantum mechanics seem to be incompatible at such energies, from a theoretical point of view, this situation is not tenable. One possible solution is to replace particles with strings. String theories are quantum theories of gravity in the sense that they reduce to classical general relativity plus field theory at low energies, but are fully quantum mechanical, contain a graviton, and are believed to be mathematically consistent.